Okay, so how is everyone today? Good?
Good.
It's Friday. All right, today's the 19th there. So we've been talking about polar coordinates, and we're still talking about it. And here's for a few minutes, we're going to talk about just sort of the nuts and bolts of polar coordinates to make sure that, pardon me, to make sure that you can have a intuition about what these things mean. Excuse me. All right. So in rectangular coordinates, which is to say not polar coordinates, among other things, is that if we say the following, if we say let a less or equal to x less or equal to b, and c less or equal to y less or equal to d, and we sketch that on a rectangular axis, then, well, it looks like this. So if I find x exactly a and x exactly b, then that might be like here and here. And I've drawn that on the x-axis there. And then I could find, ignore the horizontal axis and just look at the vertical axis, and I could, draw this. So maybe C, that's where y is C and where y is D. Okay, then that's how they are individually. But then if I wanted to know on the plane, what are all the points x, y that satisfy both of those conditions? That satisfy them both? In the end, everything between these lines, everything between those lines are the stuff that satisfies the first condition, right? And then I could make two more lines. And everything between these two lines is all the stuff that satisfies the second condition. So what's all the stuff that satisfies them both? That rectangle. Which is, more or less why that's called a rectangular coordinate system. So in a polar coordinate system, it's a bit different, really. So in polar, if we say let say I don't know, 1 less or equal to r less or equal to 3. And not 0. I don't. Let's do pi over 6 less or equal to theta less or equal to what am I trying to say? Next one, pi over 3. So if we do that. Now we want to sketch it, but here's the deal: is that this vertical line is what a constant x value looks like. So that's a constant x value, and here's a different constant x value, that vertical line. And then this horizontal line is a constant y value, and this horizontal line is another constant y value. So my question to you is that in the polar coordinate system, what is a constant r value? a circle. So this set, the set of all radii between 1 and 3, that's the set of all points between two circles. That's what that means. It's an annulus, yes. So like, there's the circle of radius 1, and here's the circle of radius 3. So to satisfy the first condition, you've got to be outside of the little circle and inside of the big circle. Now, what does a constant angle look like? Well, that'd be a line proceeding from the origin and away from the origin on that particular angle. So, like pi over 6, that's about, like down here. And pi over 3, that's up here. And so, this is this little circle is radius 1, and this bigger circle is radius 3. So to satisfy the first condition, you have to be between the circles, and to satisfy the second condition, you have to be between the angles. So can you see the part of the thing that satisfies both conditions? So it would be this bit. Okay, so I gave you a printout there, and you can see it, right? You can see the little things there. So instead of like graph paper where everything is little bitty rectangles, like rectangular graph paper, notice that the little bits are shaped like this. Right. So that shaded region is the stuff between two radii and between two angles. And then you could say, well, you could, for example, select this region. And that would be all the stuff between, just not that part, but just this new part that I shaded. That's all the stuff between two radii, between radius 1 and 1.5. That's what that is. And then if I instead say take this much, this red here, and shade all of this, all the way out to infinity, then that's the set of all points between two angles. Okay, good. So any question about this? Okay, so then I guess I'll do it here. So last time we established two formulas. Okay, so then one of them was that if we have a circle, and this circle has radius r. That's radius r. And if we select two angles, for example, these two angles, that one and that one, and we want the piece of pie there. We want just this here, the piece of pizza, the slice. So such a thing is called a sector. And if we say that the angular measure from here to here is delta theta, we could name that angle beta, or alpha, and this one beta, say. Then delta theta would be beta minus alpha. Then what's the area of that thing? So that's a formula we came up with last time. What is it? Yes, d theta, right? Delta theta. So 1/2 times r squared, and then times delta theta. Okay, so we established that last time. And we also established that if now we have a circle, and in fact it's got a center, and then we delete a circle out of it, like this. So those circles are both centered at the same place. I'll say that the little circle has radius r1, say. The big circle has radius r2. And then the change in the radius, just that much, we're going to refer to as delta r. So delta r. And then if from there, from the center, we select two angles again, we say, okay, angle, angle. And this has angle, say, alpha, and this one beta. And if we call the angular change delta theta, then that tells us, that we could be looking at this. That piece. And then we came up with a formula for that one as well. So what's the formula for the area of that one? Uh-huh. Oops. So R1 plus R2 over 2 multiplied by what? Delta R, delta theta. Okay. So interpreting that's saying that the area of that annular sector is the average radius multiplied by the change in the radius multiplied by the change in the angle. Okay. Good. Any question about that? Okay. So now, here's the main trick for today, the main idea. So I'm going to draw in two columns, side by side. So like this. So the left side is going to be rectangular. This is something that you know already, and that is that if I say let f of x be defined on a to b, then I can draw a picture. A to B, and I'll say that it happens to look like this. So that's the plot of y is f of x. And if we want that area, if we want to figure out the area under the curve, if we want to figure that out, then this the standard way to go about doing it is you say well, is it a rectangle? Because all I know is rectangles. I don't know anything else. So is it a rectangle? Ah, it's not a rectangle. Darn. So what I'm going to do, is I'm going to cut it into pieces. So I cut it into pieces, and just for sake of the drawing, I'm going to cut it into 4 pieces because that, makes my life easier. 4 because humans can visually cut things in half pretty easily, so I can do 4 by cutting it in half and then cutting the pieces in half. And then for each region now, for each region, I'll select a point. So maybe I'll select that point and that point and maybe that point and that point. So there were 4 little regions, so that amounts to a selection of 4 points. So that input right there produces this output right there. That input produces this output, this input, that output, this input, that output. And now for each of those outputs, I'm going to make a rectangle of that height. Okay, there's that rectangle, there's that one, and there's that one. So those are all 4 at different heights. I should have selected slightly different points, but whatever. 4 different rectangles, okay? 4 different rectangles, and the thing of it is because we're in a rectangular coordinate system, I know about rectangles, right? And in particular, I know their areas. So this in the picture they look evenly subdivided, but they may not be evenly subdivided. One of those rectangles might be a little less wide than the others, and others more wide than others. So then I could say that width there of that first one is delta x1. This one is delta x2. This one is delta x3. This one is delta x4. The width there, and then if these input points are named C1, C2, C3, and C4, so those are the names of those inputs we selected. So then what's the name of the output corresponding to input C1? F of C1, right? Because F is the name of the machine. So how high is that first rectangle? F of C1. So each one of those rectangles, now we can view them individually. So for example, that leftmost rectangle has a base delta x1 and has height f of c1, right? So its area is the product of those two. So that one times that one. Okay, similarly, the next one's a little bit shorter. Delta x2 is its base, and its height, is going to be f of c2. The next one's a lot shorter. So this is delta x3, and that height is f of c3. And then the next one's a little bit shorter. So delta x4, and that one is f of c4. And so we can find the area of all 4 of those, and then we can add them all up. And that's not the exact area under the curve. It's just an estimate, right? But how can we make it more accurate? Use more rectangles. Okay, so then for whatever if you're working on an engineering problem, there's some number of rectangles which is going to be enough, right? So maybe it's 10,000. For example, Boeing, they make airplanes, and they have to do physics and engineering modeling on the surface of the airplane. And the way they do that is they actually approximate the surface of the airplane with little bitty triangles. Okay, mathematically, you can imagine it actually consists of infinitely many infinitesimal triangles. But in actual fact, Boeing can get away with using probably just a few tens of millions of triangles. That'll be enough. Okay. So we could. That's just 4, but really, imagine that it's n. So then, adding up the areas of all n rectangles, we'd say, well, we'll sum from I as 1 to n, f evaluated at ci multiplied by delta xi. So that's our estimate for the integral. For the area under the curve, and then we say, okay, well, how do we even for big N, that probably won't be exact. So how do we make it exact? Well, we say let the number of rectangles go to infinity. So you say, okay, limit as n goes to infinity of the summation from I is 1 to n of f of ci delta xi. And then, we've got the standard joke there that, oh look, we've got a formula there that has Greek symbols, and we're going to compute a limit. And as a result, all the Greek symbols turn into Latin symbols, right? So what does sigma turn into? S, right? And what does delta turn into? D, haha, right? Okay. It's like the oldest joke in calculus. Now, there's a little bit of sleight of hand that's going on here because this thing that I'm writing here is slightly sloppy because it also means that the width, well, I'll say it like this: all delta xi have to go to 0. So what that means is that it's possible to have infinitely many rectangles, but like leave one of them like really big, and we're saying that no, in fact, all of them have to get small. Okay. What I want you to see here is that the integral, this point of view of the integral in a rectangular coordinate system is saying that hey, you take any shape, and if you look close enough at any shape, then in fact it actually just consists of infinitely many infinitesimal rectangles. And because we know the area of a rectangle, we can find the area of that shape by cutting it into rectangles. Well, so now in polar coordinates, what if I say let r equal to f of theta be defined on alpha to beta. So now I'm going to draw a picture. So now we're talking about a function of two angles. So I started out drawing this picture by drawing a constant input A and a constant input B. I drew those. So now I'm gonna draw a constant input alpha and a constant input beta. Now alpha and beta are angles, so what does a constant angle look like? A ray from the origin. Okay, so then I'll say that this is that's alpha, and this is beta. So alpha and beta, and so we've got some point here. We've got some point there, and now I need to, meander my my way over to there somehow. So something like this, blah, blah. So like that. Okay, and can you see this shape that's between the two angles? And it has the origin, the pole, at its pointy bit there, and then we've got that function. So can you see that shape? That's what we want to find the area of. We want to find the area of that shape. But the deal is that, we're not in rectangular coordinate systems, so we're not going to cut it up into rectangles. We're in a polar coordinate system. So instead of subdividing, well, we're going to subdivide the inputs. And when you do that on rectangular coordinates, you end up getting these things. But when you subdivide the inputs among the angles, you end up getting little angle bits. So I'll subdivide it once, and then again. So I subdivided it once, and then again. And now, for each little fan, each little bit there. So like, see that that little bit, that little bit, that little bit, that little bit. There's 4 little bits. What I want to do is I want to select some angle that's in between those two. So the way I'll help you visualize it in this case is that for each little piece of red graph that's in between two, I'm going to select 1 point. So select 1 point on each of them. So how about that point for that one, and that point for that one, and that point for that one, and I don't know, this point right there for that one. So now, going through those points, so the way we did it over here is we drew a constant output, a constant y. Now a constant y is a horizontal line segment. That's what that is, a constant y. But the output symbol here is r, right? Meaning radius. So what does a constant radius look like? An arc of a circle, right? So what we need to do is we need to draw an arc through each one of those. Okay, so we're going to draw an arc that has the same radius. So here it'll look like this maybe. This one like that. This one maybe like that. And this one maybe like that. So a constant radius. All right. So now, the way that we're going to do it is just like we said that, you know, we subdivided the inputs and said, okay, the change in the input for that one is delta x1, delta x2, delta x3, delta x4. Now we're going to change the inputs, but the inputs are angles. So instead of calling them delta x1, what am I going to call this one? Delta theta 1. So this will be, you know, going this way, this will be delta theta 1, and this one will be delta theta 2, and this one will be delta theta 3, and this one will be delta theta theta 4. Okay, so we've got some delta thetas there, and so we could name the angle that happens to go through each one of those points, right? So then there's an angle that goes through each one of those points that we selected. Okay, and for lack of anything better, I'll just again call them C1, C2, C3, and C4. So this one, you know, that's angle C1, that's angle C2, that's angle C3, and that's angle C4. Okay, so so now that drawing's starting to get busy. So there's four little bits in there. I'm going to pull one of them out so we can look at it very closely. So pulling one of them out looks like this. Like that. And now, you know, this is angle C1. So that's angle C1. And then my question is what is this this thing right here? What's that radius? How do we calculate that? Well, how do we calculate any point that's out here? So like if, in the rectangular thing, if I point here at input C2, how do we find the output? Yeah, we plug it into F, right? F says, how tall are you? So if I take this angle C3, how do I figure out what the radius is at that point? You plug it into F, right? Same story as before. So that means that this radius, that radius right there, is F of C1 is the radius. Okay. So wow. So you're and we said that this angular change there is delta theta 1. So what we're saying is that that's a constant radius between two angles. And the radius is f of c1, and the angular measure is delta theta 1. Well, we've got a formula 2 pages ago for the area of that thing, right? What's the area of that? so from the previous page, that's half r squared delta theta. So what is it on this page? Right, half f of c1, square that, and delta theta 1. But do you see that there's nothing special about having taken the first one? The second one is just like the first one, except we changed the index to 2. So the second one would have area half f of c2, square that, and then multiply by delta theta 2. So as a result, the area of that estimate is the sum from I is 1 to n of half f of ci square that delta theta I. So that is to say that our estimated area is, the way that we find it, is we find the area of each individual sector, and then, then we add them all up. But, in the picture we use 4 sectors, and that's not exactly the area. So how could we do better? More sectors, right? And for any engineering problem, some number of sectors is going to be sufficient. And in calculus, we say, well, I don't even want to stop. I just, what would happen if there were infinitely many infinitesimal ones of them? Which is to say, all right, let's calculate the limit as n goes to infinity of the summation of I is 1 to n of half radius squared delta theta I, like that. And then, same joke as before. Haha, it's a formula with Greek symbols and then a limit and then the Latin symbols. Haha, so it'll be integral, and then what will be the limits? Alpha to beta. And then it'll be half f of theta, square that, d theta. So it's the exact same idea. So what I'm telling you is that in the rectangular view, you look at a shape, and if you look at it closely from the calculus point of view, that shape actually just consists of infinitely many infinitesimal rectangles. That's what it is. But if you are looking at a shape, but you're reckoning it to be situated in a polar coordinate system, and you look at it, and if you could get out like a microscope and look at it real close, then that shape actually consists of infinitely many infinitesimal sectors. And what I want to point out is that this is a pervasive view in calculus. That you just take your favorite shape, okay? And you say, my favorite shape is a rectangle. Okay, well then let's consider that thing we're looking at to, even though it's not a rectangle, it can be decomposed into infinitely many infinitesimal rectangles, or infinitely many infinitesimal sectors, or if you have a banana coordinate system, infinitely many infinitesimal bananas, for whatever that means. Okay, and I want to impress upon you that this is not really that surprising, because after all, for any one of us, if we were to get out a microscope, you would quickly realize, oh my goodness, I actually consist of just a lot of cells. That's what I am. And then if you got an even better microscope and started looking close, you would say, my, that cell actually just consists of a whole bunch of atoms. It's incredible. Okay. So, to that end, we can now summarize the formula for area. We can say this thing. That if we say that let r equal f of theta on alpha less or equal theta less or equal beta. Okay, then the area of that description is so that area right there, its formula is integral alpha to beta half, and then usually it's written r squared d theta. But understand that's f of theta squared. Okay, any question about that? All right, so then let's do a fun one. So, remark or example, I could say. Find the area which is inside R is twice will work. R is twice cosine twice theta, and outside R is 1. Okay, so one of your assignments was to familiarize yourself with the plots of polar graphs. So just like in rectangular coordinates, you should know what y is x squared looks like, and you should know what y is log x looks like, and all of that. You also need to know, have a catalog of knowledge about these things. Okay, so then we'll start with a simple one. What's that when you plot it? As a circle, right? So that one's easy enough. So if you plot it, it looks like this. Okay. And then this one is a little trickier. What does this one look like? What's this one going to be? So generally, this one right here fits in the pattern. R is some constant a multiplied by the cosine of n theta. So what's going to happen is that this whole thing is going to fit inside of the circle of radius a. So it's all going to be in there, because cosine, what's the maximum value of cosine? 1, and the minimum value is -1. So this could never get, this thing could never get further than a from the origin. So this thing could never get further than 2 from the origin, right? It can't get beyond that. So it has to fit inside of a circle of radius 2. And furthermore, this n, what that ends up representing, it's a number of petals. So this is a flower, a rose, of how many petals? 2 is a good idea, but it's not 2. It's actually 4. It's going to be 4. Because, well, yes. And so what it is that there's a parity issue. Parity meaning odd versus even. So when n, the multiplier, is odd, there will be that many petals. So like cosine of 3 theta has 3 petals, and cosine of 33 petals, cosine of 33 theta has 33 petals. But when it's even, you have twice that many petals. So like cosine 2 theta has 4 petals, but cosine 3 theta has 3 petals. But then cosine of 4 theta has 8 petals, right? Okay, so then this is a rose fitting inside of a circle of radius 2 of 4 petals. So that's something that you just have to know. So you need to know what these look like. So this one is going to look like this. So here's the circle of radius 2. Okay, so what I draw has to fit in there. And then because it's a cosine rose and not a sine rose, that means that, you could figure this out by just plotting points, but that means that its first petal is going to be aligned with the x-axis. So it's going to look like this. So you start from here and then go out to the origin. And then from the origin, you proceed this way. And then from here, you go back to the origin. And now you go to this way. And from here, you go back to the origin. And now you go to the top. And then from here, back to the origin. And then where from here? Back to where you began, right? So that's a cosine rose of 4 petals sitting inside of a circle of radius 2. Okay? Fine. So we know what both of these things look like now. So individually, which is to say that, oh, that one looks like that, and that one looks like that. But the thing is now we need to situate them both. We need to situate them both on the same on the same axis, right? So we can figure out what could we possibly be saying. We want it to be inside the one and outside the other. Okay. So a sketch of what we must be talking about. Is that, well, there's 2 circles involved. On the one hand, there's the circle of radius 1, which is just that, right? And then on the other hand, there's the circle of radius 2, which the rose has to fit inside of. So here's the circle of radius 1. And then here's a circle of radius 2. This isn't part of the drawing. I'm just, this isn't part of the graph, I mean to say. This is just going to help me draw the graph. Okay, so now I need to put that cosine rose on there. So it'll look like this. Oops. And then doing this reminds me that when I was little, I had a toy called a spirograph. Have you ever heard of that? That's more or less what this is. Okay, so then we want the area that is going to be inside the red and outside the green. So can you see what area it is that we must be talking about? Okay, so specifically, there's like 4 little bits of it. There's that bit, that bit, that bit, and that bit. Okay. And our mission, should we choose to accept it, is to find that shaded area. Now, this is a symmetric picture, which means that if we could find the area of just one of those bits, then we could find the area of the whole thing by multiplying by 4. So we're going to find, here's the strategy. We're going to find the area of just say that one, and then multiply by 4. All right. So, in order to figure that out, I need to draw a big exaggerated version of it, so that it's easy to see. So, I'm just going to draw the one that's on the right there. So the circle, exaggerating the circle a little bit, is going to look like that. And then the pedal like that. Now I'm drawing it in an exaggerated way on purpose. So remember the definition. What it does is it integrates between two angles. Okay, that's what the area definition does. So having a look at the picture, we need to figure out what two angles could we possibly be referring to. And remember that angles, constant angles, are represented by rays from the origin. So here's the insight concerning the green and the red. Well, and also for that matter concerning the integral formula. Do you observe that we integrate between two angles? And concerning this picture, do you observe that there are two intersections? So if I draw the rays passing through those, then that's some angle alpha, and that's some angle beta. Now here's the deal. Here's the deal. If we integrate the red function, just the red one, we will get the following. So integrating the red, we'd get a shape that looks like this. And then, you know, something like this, if we integrated just the red function. What if we integrated the green function? What shape would we get? We get you know, something that's kind of like this. And the truth of the matter is that in fact we don't want we're not actually interested in either one of those areas, because the whole shape together actually looks like this. You know, exaggerated. And what is it that we want? We just want this bit, right? So it's kind of like a, you know, like an ice cream cone, and we just want the ice cream. You see what I'm saying? So how can we get just that? Right. So you know, we got a little formula here. The one that we want. Okay, the bit that we want, the ice cream, if you like, is going to be the whole big one. And then we need to subtract away the little one. And before we can do anything at all, we've got to figure out those angles. So how do we figure out those angles? Well, generally speaking, if you're looking at a picture and you want to find intersections, then what's the corresponding algebraic thing? Yeah, we have to solve an equation. We want to solve both of those equal to each other. So we want to solve twice cosine twice theta equal to 1. All right. Well, dividing by 2, that's cosine twice theta is half. Okay. Now, ignoring what's in there and just referring to the thing that's in there, we could just call it t. What would you have to input into cosine so that the output would be half. Pi over 3, right? Pi over 3. So as a result of that, that's saying that one of the solutions is that twice theta must be pi over 3. Okay. Now, of course, there's infinitely many solutions to this, and we're saying that this is one of them, of the infinitely many. Is this one of the just 2 of them that we need? If we solve for this, this would be saying that theta is pi over 6. Could that reasonably be one of them? Yeah, right? That's that one. And now you should be able to deduce by symmetry, what's the other one? Nah. If it was 11 pi over 6, that'd mean you're going this way. We need to go this way. We need to go to pi over 6. So we would have to be coming from what? Positive pi over 6? Negative pi over 6, right? So that's saying that the picture actually looks like this. So we're saying that this one is pi over 6. This one is negative pi over 6. This one is like that. This one is like that. So finally we have a means to calculate. So the area of this is going to be, we have to do 2 different integrals. Okay, so it'll be the integral of the red one. So that'd be integral, and then what are the limits? Negative pi over 6 to pi over 6. And then we have to integrate the big one, which is twice cosine 2 theta. But is it like this? So in fact, I made a lot of errors here. So what's the formula? So I'm putting the big one here. So twice cosine 2 theta d theta. So is that it? No, right? What do I have to do? Oh, okay, I forgot a half. Ah, and I have to square it too, right? Remember, because what we're doing is we're accumulating sectors, not rectangles. Okay, that'll give the area of the big piece, and now we need to subtract away the little piece, so we'd have to do subtract integral negative pi over 6 to pi over 6, and then half, and what's r? 1. Oh, mercy, right? And then d theta. Okay, so that's a formula. All right, are we about out of time, I think, probably? Yeah. So you'd have to evaluate this to find the area. I leave it to you. Okay, have a nice weekend.